Thank you. Good afternoon. This talk is mostly addressed to the high end of the Mill CPU family. It's a family in the sense that the 360 is a family, and at the low end, the kinds of issues that he speaks of are essentially not a problem. I mean, an x86 can decode 4 instructions in a cycle. If all you need is 4, this is established art. It's when you're at the high end and you need to pull a whole lot more. Other talks, other times, or questions, I can remark on what we do at the low end. They are equally innovative as what we have here. This being a university class for credit, we'll do the traditional and start with a short quiz. You all know the various kinds of architectures. There's accumulator machines and stack machines and this, that, and the other. So if I give you a set of specifications for an existing chip, can you tell me what architecture that chip is? Incidentally, this is an existing top-of-the-line product from a major manufacturer. 4 cores, each one of which can handle 4 operations per cycle. You may need Freon cooling. 3,300 megahertz. Using 130 watts, that's where the Freon comes in. 52 giga operations per second. For $885 list. Anyone want to guess what the architecture of that chip is? Don't all speak at once. Someone? Yes?
Some random 8086.
But the architecture, not...
Oh, the architecture.
What is this organized? Is it a stack machine?
It's a register impoverished machine.
I'll take that one. It is, in fact, a general purpose out-of-order superscaler, which, in particular, is an Intel Xeon. Now,
Freon?
one more example. This one's got 1 core, issuing 8 operations per cycle, clock rate of not quite 500 megahertz, only 1.1 watts. Am I in the way of people seeing this? I can move over if it would help. Only 3 gig operations, but also only $17. Anyone want to guess what the architectural category that chip belongs to?
Is it a DSP?
It's a DSP, and in particular, it's an in-order VLIW DSP, and it is a Texas Instruments DSP. Now, in abstract terms, these two are very, very different. But if you compare them, which is better? Well, it's apples and oranges, of course. But over the last decade, the industry has sort of consolidated itself into an accepted figure of merit, which is a good rule of thumb. That figure of merit is performance per watt per dollar. And obviously, you do need certain other things. You need the I/O complement that you have and everything else. But just for purposes of general comparisons, this has become the standard. Now, there's our 2 cores, our 2 chips. And the out-of-order superscaler is your half a MIPS for your watt and your dollar. The in-order DSP gives you 195 MIPS for your watt and your dollar. It's a factor of 400. Now you'd think that by now somebody would seen a market opportunity in this and tried to arbitrage that number away, but that difference has been around for a long time. So why is there a 400x difference? One is simple. The Texas Instrument chip is a 32-bit chip. If you want to do 64-bit addressing space, you need the superscalar. Another is total raw horsepower. It takes an awful lot of those Texas Instrument chips to add up to the total number of ops that you can get through the superscalar. But what really makes the difference is that the workloads are incompatible. The TI chip running on a general purpose workload is truly awful. It is designed for things which stay in loops forever, software pipeline loops, and code that is just full of random flow of control and random memory references, which is characteristics of your general purpose code. It tends to be very bad on. Now, the Intel chip would make a fairly decent DSP if you could buy enough Freon. So, the fundamental problem is that signal processing is not the same as general purpose, which defined our goal and our technical challenge as a company when we started out to design a new processor from scratch. We wanted to provide DSP numbers on general purpose workloads. Well, the numbers I'm about to give you are coming out of SIM or our best guess for marketing. We do not have something which is actually for sale at this point. Take it with a large grain of salt. The particular chip is 2 cores, issuing 33 operations per cycle each, at a clock rate of 1200 megahertz, using 28 watts, and producing not quite 80 giga operations per second total. And our best guess is $85, although there's a gentleman sitting over there who probably may have a difference of opinion. That's our gold CPU architecture, one of several. I said it was a family, and in fact a dual core one. And you're getting 33 MIPS per watts per dollar out of that configuration. Now, in that list of what gold does, you may have noticed that. Can we get rid of this light? Is it all possible? Or are other people not getting glare off the screen? Excellent, much better. That number 33 is just completely beyond what existing chips do. Your x86 max out at 4 or 5. Some chips, well, the TI goes up to 8. The upper limit of anything commercial I've ever seen is like 10 or 11 that can be issued simultaneously. Why on earth would you want to put out 33 ops? Well, the answer is that even in general purpose code, 80% of all the code is in loops. And if you can software pipeline those loops, which of course is what all the DSPs do, then you have in fact unbounded ILP. You can soak up every adder you can throw at it forever. But in current state of the art, rather few general purpose chips can be pipelined, at least on conventional architectures. The solution: find a way to pipeline almost all loops, and we have done that, but that's not the subject of today's talk, and throw hardware at it. Few people realize that how little of a chip's area and power are consumed with the actual functional units, the adders and multipliers and things like that. 6% of the total chip is the usual number for that. You could double the number and still be only at 12% of the chip. The constraint is not that you can't fit more adders and multipliers on. The constraint is that you can't interconnect them and you can't feed them with instructions. This talk is about feeding them with instructions. Once you have done that, well, you've taken care of the loop part of the problem. Amdahl's law still exists, and we handle the open code, non-loop code as well, but that also is not this talk. So, if you're going to try 33 operations per cycle, peak, how are you going to do it? Well, of the various possible bottlenecks within the machine, by far, actually, the biggest problem is decoding this stuff. There's two basic models for instruction layout. You can have fixed format instructions, where every instruction is the same length, your typical RISC instruction set. They are dirt easy to parse. You just drop the thing into a decoder, and the next one into a decoder, and the next thing in the decoder, and away you go. Bob's your uncle. But if each instruction is 32 bits, and you have 33 of them, the total space is 132 bytes. That's over 2 cache lines at 64 bytes per cache line. And you're simply not going to be getting 2 cache lines per cycle out of your top-level instruction cache. So that's pretty hopeless. It's an ouch. The other side of that problem is instruction cache pressure. You can't have unlimited instruction cache. Everybody needs more instruction cache, but the bigger they are, the further they are from the functional units, and the longer they take, and you start paying in your cycle time. Well, if you have a typical size of a 32K instruction cache, and they are occupying 132 bytes each, you only get 248 instructions in that cache. And as a rule of thumb, you need at least 1,000 instructions in your top-level cache, so we're a long way from that. Now, the alternative is variable length instructions, like your x86 instruction set. They are hard to parse. Intel is very, very good at heroics. And they throw hardware, and they throw power, and they throw everything else at parsing, and they only are able to decode 4 instructions at a time, and then only if it's a restricted subset of the instruction set, because if some of the really lollapalooza instructions in the x86 instruction set, you get 1 out, maybe. So, we actually have got a very compact instruction set in coding, and we run around 15 bits per operation, per add, per multiply, per load, whatever. On the average, we run around 15 bits. We put an awful lot of effort into being compact because of this instruction cache problem. And that times 33 ops, well, we're still around a whole cache line as per cycle, and we really don't want to do that. So that's a little painful too. And the instruction cache pressure, well, we've doubled the available number of operations or number of instructions in the cache, but we're still nowhere near 1,000 instructions. So let me digress a little bit in order to explain how we get around this. First, back at the very beginning, what is it that we're handling? We're handling a stream of instructions, Mr. von Neumann and company, which the location in the stream, in the sequential thing, is indicated by a program counter. You pull an instruction out, drop it into decode to figure out in terms of signals what the rest of the machine should do, and then you go execute those signals. That's the logical view. The real world doesn't work like that on modern machines, because you have to grab more than 1 instruction per cycle. We call a common term, actually, the group of instructions that you're going to grab per cycle, a bundle. And the hardware will grab that group, a whole bundle, out of the instruction stream, where the start of the bundle is indicated by the program counter, drop it into decode, and that in turn winds up being fanned out to multiple operation functional units. If these are fixed length instructions, decode is easy. You simply have 1 decoder for each position in the bundle. drop them in bit to bit. This is why RISC was able to fit in a chip back at the beginning of the RISC days, and away you go. If, however, now, they're easy and big, yes. If you go for variable length instructions, well, you start having an issue. Where does the next bundle start? This bundle along here, how many bytes that is varies from cycle to cycle. And we need, if we're going to get the next one in the following cycle, we need to be able to find the end of it. We also need to be able to find the start points of each of the instructions within the bundle. That has polynomial cost. And indeed, this is why Intel is not able to get more than 4. Well, polynomial is not fine if n is 3, but it's not very fine at all if n is 30. So we need a way around that. Well, here was the first insight. Because it's polynomial, you can parse 2 bundles of length n much faster, much easier, much less power, much less trouble than 1 bundle of length 2n. Okay? Just normal polynomial. So, split each bundle in half and have 2 streams of half bundles. That's what it looks like. You have 2 program counters, one pointing into each of the half bundle streams. Each one feeds its own decoder, this one handling that, this one handling that, but the decoders only have half the load. They're not trying to do 30, they're trying to do 15. Well, welcome to polynomial, that's a big good thing. There are 2 physical streams and 1 logical stream. This is a single thread of execution. This is not vector arithmetic. This is not a GPU. It's this kind of thing that you're doing in your laptop or whatever. It's a single thread of execution with the sequence of instructions split up into 2 streams. The problem, of course, is how do you branch it? You've got 2 program counters, and if you're going to do a branch or a call, you need to be able to send both program counters to their new location. Well, a branch operation carries an effective address. But if you try and have a branch operation with 2 effective addresses in it, well, suddenly your code started to get bigger. And then you have to think about what does a function pointer look like when it's got 2 addresses in the function pointer. This doesn't work very well. Well, to explain that, I need to back off a little bit and introduce a term that most of you will be familiar with, the extended basic block. These are sometimes called superblocks. This is a sequence of code which has got a single entry point called the head and may have multiple exit points where it goes to someplace else. We are unusual in that we permit embedded calls inside an EBB, but that's not relevant to today's talk. So your 2 program counters are actually describing not so much a stream of instructions as a sequence of EBBs. We enter 1, that will branch to the head of another, that will eventually go to the head of another, and so forth. And just like there's an EBB in the full bundles, there's also a pair of EBBs in the half bundle streams. So there's 2 of them, as shown. The branches can only target an EBB entry point. This includes calls. It is not possible to jump into the middle of it. By definition, that's what they are. So, take 2 of our half EBBs. This is color-coded to indicate the 2 half bundles which will decode and issue in the same cycle. The 2 blues will go together. They are actually part of the same instruction. This was split in half. the two purples will go together, and so forth. So that's the color coding merely to indicate which of the two halves belong together. They're organized from lower memory to higher memory, as usual. Execution order. So you rotate one in memory. Now one of them executes toward increasing addresses, and the other one is going to execute in terms of decreasing addresses. Notice we still have them color-coded. Those are run together. Now, join them together head to head. The entry point of both, the dark blue bundle, is now at the same address. It's just that they decode in the opposite direction. Consequently, the branch problem is solved. You branch here. You branch both programs there. And one goes one way and one goes the other way. So, to take a branch, some random code, of which we are of interest is the jump operation. The jump will carry an effective address, and that effective address goes to the entry point of the now joined two half EBBs, joined into a single EBB. Note, you're now always jumping to the head of an EBB, logically, but you're jumping to the middle of an EBB physically. Now how that works. There's two program counters, they point there. We have to bring up the decode and the execute. You remember we were doing decode. We pull off the two central bundles. We move the program counters to the next bundle. The decode does its thing, sends the signals to the execute. Execute executes. Pull off the next pair. Down and execute. And so on. There we go. And that will keep on going until somebody does a branch whereupon the two program counters both go off to someplace else. Yes?
The cache lines fit into this?
Well, let me get to it. That'll come up in a minute. The short answer is that there's two caches, one for each decoder. Now, for historical reasons, internally, our two streams we refer to as the execute or exu flow stream and the flow stream. And in fact, all of the operations that are things like adds and multiplies are in one stream, and all of the operations that contain effective addresses, such as branches or loads and stores, are in the other stream. And this winds up giving us a pretty good bandwidth balance between the two sides. So at XPC there is the program counter for the XU side, and FPC is the program counter for the flow side. And when you take a branch, you go to the entry point, increasing addresses this way, decreasing addresses that way, but both program counters go to the same place. After some number of cycles later, the program counters have diverged. Physical layout and cache. Everybody needs to get their cache as close to the decoders as they possibly can, because there's a critical distance. That critical distance is from the far side of the cache to the front side of the decoder. Wires are time. So you can only get those so far apart, and that's what puts your upper limit on either paying for it in your clock rate or alternatively paying for it in the size of your instruction cache. Now, you can, in fact, have a bigger cache. But you also wind up with a bigger critical distance. This is what the mill looks like at the same abstract level. The two decoders are on either side of the execution units, and outbound of each of them are the two top-level instruction caches. That's our critical distance. You see it's the same as the short critical distance up here on the left, but the total capacity is the same as the large critical distance. We have doubled the instruction cache capacity at no increase in per operation power, area, or heat. Now that gets us down to having a bundle in the decoder, a half-size bundle in the decoder. Now we have to take the bundle apart. The bundle is itself variable length and filled with variable length operations. We issue one instruction per cycle, disregarding stalls, of course, and that will be two half bundles. There can be a large number of independent operations, a grand total of 33 on that gold that I showed you. But they all issue together. We are an in-order, statically scheduled machine, like a VLIW in this respect, and they execute in parallel. The internal structure of each bundle, every bundle starts with a header. Following the header, there's some number of independent blocks and containing operations. And the operations in any single block are all exactly the same size. They're fixed size within the block. Consequently, if you can isolate a single block, they are easy to decode just like any other fixed size format. So the problem reduces to isolating blocks. Each one of those blocks is a variable size. They may not all be present. The machine bundles are byte aligned, but the individual operations, and hence the blocks, are bit aligned, and that means there's usually an alignment hole in the middle. Not yet wasted bits, you'll see later. So, how that generic form gets decoded. Assume magically that you have an instruction buffer that has got a left-aligned bundle in it. Bundle buffer probably would be a better term. That header contains, among other things, the byte count of the whole bundle. Consequently, we can send that, furthermore, it's in a fixed position here, so it's easy to get out. We can send that byte count to a bundle shifter that in one cycle will move the whole thing over and bring in the next bundle. We don't have to parse it to figure out how long it is. We tell it how long it is. The byte count is right in there. Actually, it's a tap count on the shifter, but that effectively it's a byte count. Now, in addition, besides the byte count, the bundle byte count, there is a operation count for each one of the blocks. There's something that says we've got 3 operations in block 1 and 5 in block 2, or etc. This is all encoded in that header. Now, the header itself is fixed size. Consequently, if we have this thing left aligned in a bundle buffer, that point is known. Because the header is fixed size, that point is fixed. Consequently, we can drop all of the putative block 1s, all of the things that might be a block 1 operation, into block 1 decode. Say that the maximum number of block 1 ops that the machine can handle is 9, just to pick a number. Well, we can drop 9 hunks of bits into block 1 decode. There may only be 3 of them, but we'll figure that out later and throw the excess away. So we can immediately begin decode of block 1. In addition, because we know how many are actually present in block 1, we'll send that count to that decoder and shifter so it knows how much to throw away. In addition, because we know how many there are, we know where that is. And at the same time as we're shifting the whole bundle, a different shifter is going to be starting there and shifting block 2 into a block 2 buffer. Well, 1 cycle later, this is what you got. The whole bundle shifter shifted our whole bundle over. But if you stop and think about it, this is the header of the following bundle. If you stop and think about it, if the header is left aligned in the bundle buffer, then necessarily the end of the previous instruction is right aligned in the bundle buffer. We pull in both of them along. Consequently, we know where block 3 is. And we can drop all of block 3 into its own personal decoder. Block 3 is solved. Meanwhile, we had already shifted block 2 into block 2's own buffer. That's properly aligned, and that gets dropped in. Now, I've shown it for 3 blocks. It happens on the mill that each side does in fact have an encoding with 3 blocks, because it turns out this is all we needed. But the general principle here is applicable to an arbitrarily large number. Each cycle you're going to get 2 more blocks working in from both ends. We decode from both ends of the bundle. 1 in the first cycle, block 1, and 2 every succeeding cycle after that. Now, I mentioned that alignment hole in the middle. Any machine with a statically scheduled layout has to deal with the situation that there's nothing for the machine to do sometimes. We're in the middle of a floating point multiply, and there ain't nothing to do until we're done. And this is a standard VLIW problem, and every VLIW problem has some way of encoding how do you do a no-op cheap, because you don't want to have a whole full-size bundle full of nothing but no-ops. So in our case, we encode what's called a lag count in the alignment hole. If that's 0, the alignment hole value refers to the other side. If that's 0, he issues immediately. If, on the other hand, if that's 1, he lags for 1 cycle before issuing. Each one encodes the lag of the other side. Consequently, no-ops, because they're in fact encoded in the alignment hole, cost nothing. They're already there. Now, of course, if it happens that you don't have an alignment hole because all the bits happen to line up exactly the right way, then you have to explicitly encode it. And yes, the instruction set supports that, but it happens extremely rarely. Hello? There we go. Now, putting all this together, I'm going to give you a very rough sketch of the front end of the mill pipeline. Instructions start out in memory or the L2 as lines. Standard cache layout. The prefetch, we have a precise prefetch. This talk will also not address prediction, but our prediction machine has a precise prefetch. It's not an approximate or algorithmic prefetch, it's precise. And the amount of time it takes to get from memory, or L2, as driven by the prefetcher, it does vary. And the stuff will eventually wind up in your L1 top-level instruction cache, still as lines. From there, a separate step is fetch to get lines from the L1, and that is the cycles F0 through F1 and F2, because it typically takes 3 cycles to get a value out of the instruction cache up to where you're going to use it. This is pretty standard in terms of physical layout. And you'll wind up in the L0. We are unusual in that there is a top-level instruction cache, which is a level above the logical level on the data side. It's much smaller, it's fully associative, and you can think of it as being a transient buffer for instructions as opposed to a full-scale cache, but it's a cache. Now that has a 1-cycle delay to go into the bundle shifter, the top level of what you saw a few slides ago. And that's in the D0 cycle, which immediately follows the F2 cycle. The bundle is taken apart in D0, D1, and D2. There is no issue stage. That's where it would appear. And things go directly into the adders as operations. And as with any execute pipeline, your simple things take 1 cycle and more complicated things take longer. There's no retire stage either. So the add-to-add data flow time is 0 cycles. I can have a full data flow dependent add cycle after cycle after cycle after cycle for a 1-cycle add. And we have a 4-cycle mispredict penalty if we're coming out of the L0. We are commonly coming out of the L0 in cases like, for example, you've got an if-then-else saddle and you went down the wrong way. And both sides will be in the L0s, and that's a common situation. If it's not in the L0, you're going to have to add the two and a half, actually, in a peculiar way, cycles to get out of the L1. And if you miss there and wind up going all the way to DRAM, well, you can suck your thumb for 400 cycles. So, in sum, the mill uses a split-stream, double-ended decoding technique. Because there are 3 of those blocks on each side, there's a total of 6 blocks in each. And over 33, this means that each block has, on the average, 5 or 6 possible positions to hold an operation. But because the decoder only has to deal with 3, we have no greater problem, and in fact substantially less problem than an x86 has to get a 4 done. So in essence, we are decoding 33 individual ops, maximum peak, of course, at full speed. There are 2 program counters. They're following 2 instruction bundle streams. They are drawn from 2 instruction caches. They feed 2 decoders, one of which runs backwards. Both bundles are parsed from both ends. For each side, the instruction size, 15 bits times 17 ops, not times 33 ops, because we split them. Well, that's only 32 bytes. And that's tolerable. The memory hierarchy can feed 32 bytes to a decoder per cycle without that much trouble. I mean, other chips do it too. The instruction cache pressure, because we have twice as much cache between having small operations and twice as much cache, we're over that magic number of 1,000 instructions per in the cache. The decode rate, 30 plus operations per cycle. This is instruction encoding. The stuff that I talked about here are things that have gone in the patent filings. We are madly in the process of doing more patent filings, and while I welcome questions, some of the answers will be, I'm sorry, but the patent for that hasn't gone in yet, and I can't talk about it, but I can talk about other aspects of the mill or more about this if you see fit. Coming up in Usenix, we're going to be talking about the architecture of the machine, the basic category. Remember when we started, there was a VLIW chip and there was an out-of-order superscalar. The mill is not one of those categories. It is a belt machine. That's a new category. And it has, well, let me put it this way. There are no general registers, and the programming model is quite different. And that'll be presented at Usenix. Coming up in September, we'll be talking about the way our memory systems, subsystems works for the IEEE. And we have a technical mailing list that you can sign up for, and you'll get announcements of white paper availability and things like that. This is not a marketing mailing list. We're quite a long ways from having something that we could market, so we won't be marketing to you. This is technical. Questions? Here, let me leave that up. Questions, comments? What would you like to know? Yes?
What's the issue for not generalizing it to n streams? Is it the n-dimensional memory you would have to have?
Ask the question again.
Why is there only 2 instruction streams and not n? So could you generalize it to n streams and...
You certainly could, but only with 2 can you get one address for 2. Now, if we had n-dimensional memory and we could go in 4 ways, but Samsung just turned me down with my suggestion that they do a hypercube memory, and I don't know why.
Okay, more questions?
Yes?
How much of an improvement do you think there is decoding 30 instructions rather than having a SIMD that's 30 wide for, say, spec FP?
30 wide VLIW on spec FP.
The difficulty is usually, in some ways you can look at the way we encode as being very VLIW-like. The real problem is that while you occasionally need 30 plus instructions, you frequently need 3. And you want an encoding which is compact for the 3 case as well as for the 33 case. And it is difficult to take a conventional VLIW layout and do that. In fact, that's essentially what we did. We started with a conventional VLIW layout and came up with this so that we could have the same kind of performance both for big and small. It's purely an encoding issue.
Generally, the basic size of basic block is quite limited in the general integer applications. How do you cope with the extending the size of basic blocks?
Well, as with most approaches to superblocks, which is not our technology, this is a well-established compiler technology. Most of some approaches to superblocks attempt to get the maximum length of EBB that they can. And there are standard techniques frequently called if conversion for doing so, where if then else's are folded down into data flow as the form of conditional moves or select operations. We have a select operation, not a conditional move, and so consequently we do the same. There are 2 fundamental problems of taking it much further than what you'll read in the literature. One of those problems has to deal with calls. Calls are very frequent, and if you treat a call as being the end of an EBB, you're in trouble. We are unusual in our definition in that we do permit embedded calls even within a single EBB, but I need slides to explain how we do that. It's been filed, but without a slide, it's not something I want to take on. The other problem is how to handle exceptions and other hazards that occur in the middle of an EBB. If you're attempting to fold in and do speculative execution, which of course is what if conversion is, you have to be able to deal with the possibility that an exception happened down the path that you didn't actually take. And there are various techniques. If you want to see something truly Baroque but actually works fairly well, learn the Itanium instruction set and how they recover from exceptions. We don't do it like that at all, but we have a recovery method such that we are not subject to exceptions down the wrong path and consequently can do much more extensive if conversion and lengthening of EBBs. Again, that's another talk. More? Please.
You started out this talk talking about loops. Now, do you have any constraints then on what kinds of instructions can be within a bundle? Like you said, this isn't a vector architecture.
This
right?
is, well, it is a vector. Every one of those operations can be a vector op. Those 33, however, are MIMD independent scalar ops.
Right.
But the way the architecture works, it's a two-dimensional. There's MIMD in one dimension and SIMD in the other dimension. And so any one of those ops could be doing vector operations, except, of course, things like branches, which are inherently scalar. So it's not a vector architecture in the sense that a GPU is. It is a vector operation architecture in the sense that an x86 is a vector architecture. We are not constrained. There are many ways to organize your bundle contents. In fact, this technique can be applied to a conventional instruction set as well as a peculiar kind of thing. But the way we organize it is that we partition the operation, the entire instruction set, into two groups. All the adds are over there. All the loads are over there. Consequently, the decoders are somewhat simpler because this side doesn't have to worry about decoding a load, and this side doesn't have to worry about decoding an add. And simpler is better, lower power, et cetera, et cetera, et cetera. That's the way we do it. Yes, sometimes you wind up being totally saturated with adds and the loads side is doing nothing. But it's purely a matter of load balancing and it's well worth the cost.
Okay.
Do you reuse the opcodes?
Hmm?
Do you reuse the opcodes on either side?
Again?
Do you reuse the
Do I reuse the bit and patterns of the opcodes? Yes.
Same bit, yeah.
Which also makes things compact. There's somebody behind you, John. Somebody over there? I guess not. You're up.
Okay. x86 processors implicitly are targeting x86 existing code to run. DSP processors are implicitly targeting DSP problems and so forth. What is the target area here, or what's the instruction mix that you're using in order to make your decisions, in order to evaluate your performance, in order to evaluate how to allocate?
Target market for the family. General purpose. Typically load store heavy, control flow heavy, and not enough regularity that you can do anything useful in the line that you wouldn't deliver more loops. The lowest, it's inherently a 64-bit machine. We do not compete against 32-bit or 16-bit machines. We require the presence of 64-bit address space. So the Z80 market is safe from us. At the high end, we're way above all existing architectures. And because it's an architectural advantage, not a fab advantage, each new node, they get better, but so do we. It's architectural. One of the reasons why we did not, well, several reasons why we did not focus on the high performance computing market, the floating point market. Two reasons, really. One is that Livermore Loops, a conventional processor, does a fairly decent job, and we wanted someplace where we had a larger gain for market entry reasons. The other is that nobody makes any money building supercomputers, and we're in it for the money.
The flip side of my question, the follow-up, is that things that try to be all things to all people frequently end up not being real competitive on much of any. I don't know your design well enough to critique it. Many years ago, one of our speakers was Bob Collowell, who designed the Pentium Pro, which is basically everything Intel has introduced in the last 20 years has been
I know him well.
based on that. In his book, the Pentium Memoirs or something, Pentium Chronicles, thank you. I think he comments that he was really glad that they were constrained in a lot of ways because that let them target things. That more than any other one factor, more processor architectures have failed because they didn't accept any constraints and they wanted to be all things to all people privately. I'm told that the Pentium, the Itanium, may suffer from that during the design phase they weren't willing to accept any compromises, and thus they came up with something that was sort of a hodgepodge.
Leaping ahead to your question, I think we've adopted the wisdom of IBM. IBM realized they could not do a single processor which was all things to all men. They didn't try. They produced a family of 9 processors, which were all things to a whole lot of different men. We're doing exactly the same thing. Yes?
Did virtualization come into your design thinking?
Virtualization will control what instruction you're seeing in the caches. But once you've pulled up a line, that belongs to you. And from that point on, you decode it just like you would if you weren't in a virtual environment. Yes?
Common knowledge is that general purpose code has an ILP of 3 or 4, not more. So I really wonder how you get up to the 33, and if you do, why didn't you take 66 or whatever? How many?
Because it's only 80% of the code and there's Amdahl's law. Singh and Pat, Professor Pat from Austin, did a study in which they took alpha code straight out of the compiler in binary and worked out if they had an unlimited number of functional units and could feed them, at what point in adding more functional units would be diminishing returns. And their answer was that you actually didn't need that many more floating point units than, at least in their code sample, which was all your usual benchmarks, than what a modern machine has. You needed 4 to 6 floating point units. But they still had use for more ALUs with 24 ALUs. The parallelism is there. It's just not parallelism that will fit in a instruction window. We don't have any instruction windows. Or alternatively, all of memory is an instruction window, depending on how you want to look at it. If that 33 is completely wasted in open code. But look at your own code. How much of your code is in loops? Rather little of that code in modern compilers can be turned into software pipelines. No sooner does it have internal flow of control, or it's a while loop, or lots of other things, and the compiler throws up its hands and does not attempt a software pipeline because it doesn't know how. And you can get a PhD trying to figure out how to do better. We do not have any compiler wizardry. There just isn't any. The wizardry is in the architecture, and we can, in fact, software pipeline because of the way the architecture works. We can software pipeline through control flow. We can software pipeline while loops, and with software pipeline reductions and a whole lot of other things. One thing that I will give credit to the Itanium for, Bob Rao realized the software pipelines mattered, and that for a high-end machine, he needed to support software pipelines, hence the rotating registers in the Itanium. It was an early effort, and Bob didn't live long enough to do it again. Others? Yeah, yes.
Is your plan to program this thing using conventional languages? You're
Oh,
not.
entirely. But as I say, we're in it to make money. We're not trying to sell somebody a
I
language.
just wanted to make sure.
No, this is running C straight off the web. We've been in SIM for several years. And I mean, you got an ad, you put the ad in the bundle. This is purely an encoding issue. What I've described here doesn't care what the instruction set is, doesn't care what language. It's how do you get the bits apart?
You probably won't be able to go into much detail because this may not be something that you haven't filed a patent for yet. You sort of said this wasn't a conventional register machine. It's apparently not a stack machine. You indicated
Belt machine. Okay,
belt machine. Okay.
I love to brag about my baby. There are no general registers. The programmer's model, and bear in mind this is a model, this is not a physical reality. The model of an x86 is we do one instruction until it's finished, then we do one instruction until it's finished. But it doesn't work like that on the inside at all. But the programmer's model is this is one at a time. The programmer's model on the mill is a belt machine. The communication of data has, well, you know how a stack machine works. You shove a value on the stack, then you add the top two items of the stack and shove the result on the back. But there's no addressing of operands. You don't have to have a register in there. In our situation, the programming model is a conveyor belt. All of the operations drop their results at the front of the belt and pushes everything else along. If you want to do an ad, you can say, I want this value off of the belt and I want that value off of the belt. And they'll add it together and the result of the ad will appear in the front of the belt and everything gets shoved along again. Now when I say give me this one and this one, what I'm actually doing is I'm saying give me the third most recent value that got dropped on the belt, and the fifth most recent value that got dropped on the belt. Because every cycle, new things are being dropped on the belt and the whole thing is being pushed along. So what we're doing here is not spatial addressing, not register numbers, not memory addresses. We're doing temporal addressing. We're saying this sequence in time, its addresses change. Each cycle, the location is different. Eventually, it reaches the end of the physical belt and drops off. And if you have a value that needs to be saved longer, well, you have to move it to someplace else, and we have mechanisms for doing this. Professor Pat is producing very good papers, but another one of his papers, he took apart to see what the average actual dependency lifetime was for values produced. Again, huge mass of code using a conventional compiler and a conventional instruction set, something MIPS, I think. And he found that 80% of all operation results are used once. Period. That's it. 14% are used 2 or more times. And 6% are never used at all in this code sample. Now, as we're dropping things in the belt, the compiler is scheduling code data flow style so that the consumer is close to the producer. In VLIWs, this is a 20-year-old compiler technique, and we use exactly the same thing. Nothing novel there. If the ad has produced a result that's going to be used by a multiply, well, you schedule the multiply as soon as the result's going to be available. And that takes care of your 80, and it takes care of about half of the 14%, because half of them, the immediately following consumption is going to be soon enough that the value is going to be still on the belt. It's only the values which need to be kept for some time considerably later that need to be run off somewhere, and that is running around 6 or 8% of all operands. Now, if you've got physically a small belt, like our low-end machines, you can't be dropping a whole lot because things will run off the belt before you're done with them. If you've got something like that double gold, you need a whopping big physical belt because you're going to want to use them before they get to the end and disappear. So there's a configuration trade-off between length of belt and the amount of work you're spending running things from the belt off to temporary storage, our scratch pad, and back. And that's purely a matter of configuring a particular member of the family as to where you want to make that balance.
Does that mean that the low-end machine requires a different binary than the high-end machine, or do you JIT that?
We use another trick from IBM. I'm not proud, I'll steal from anybody. IBM in the System 38 had an awesome and very interesting capability architecture. But they wound up changing that architecture several times at the bit level encoding basis. But their mechanism for supporting that and being able to run the same code on every member that they ever built was that the final step of going from program to bit encoding was done at install time, or even in some cases at load time. So we are binary compatible, as they were, at the load module level, but not at the bit level. We've got libraries which, if you want to write a JIT for us, for example, you don't generate the bitsies at all. You generate our slightly higher level representation of what mill code looks like and feed it to our library, and our library will give you bits, which is what we ourselves use.
I've got a lot more.
We got one over here.
Your model as for this belt thing sounds to me like, remember systolic arrays? You recall that architecture?
Well,
Inspiration from them?
It is, but it's of limited length. But rather than feeding directly in the way a systolic machine would, where the data goes from producer to consumer on a more or less dedicated data path. On the belt, the values are just dropped on the belt, and 16 people can pick up the same value all at once if you've got 16 ops, which a systolic array can't do that. We're intended for general purpose code where there's no a priori predictable structure to what the access pattern is going to be. Don?
I think you mentioned that there are a lot of calls in any program. One of the main motivators for RISC way back when was different techniques of trying to optimize calls, parameter passing, particularly RISC, Spark focused on register windows that would overlap for parameter's sake. 29,000 had a stack of parameters where you always had access at some base point. Some of the RISCs had local register sets and global register sets.
No, we do not have a local belt.
What everybody agrees is that parameter passing is a big issue. Getting in and out of routines is important. Being able to return multiple values is something you need to focus on. Everything you've said sort of suggests that there's no obvious parameter passing convention, because when you call a routine, who knows what the order was that put things onto the belt, such that they may not be present in the order each time, in the same way each time the routine is called.
Well, let me digress very much slightly and tell you how a divide works. A divide is logically a two-result operation, quotient and remainder. This is a royal pain in the butt in most instruction set architectures because everything is designed and encoded for a single result going to a single register. And they use implicit registers and this and that and the other in order to solve the problem, and it's always a kludge. On a belt, it's easy. You drop 2 results. That simple. This is what function calls do, too. You can have a function call which produces well, not an arbitrarily large, it is limited, but a large number of individual results. All your output or in-output parameters get turned into results for us. You've got textually 1 result and 3 output parameters. Well, that we just turn that into a function call with 4 results, all dropped. Now, to going the other direction, which is to get arguments into the call, the values which are on the belt, we will assume that we've just computed them, so all the values we want are on the belt, but they're not at all necessarily in order, and they've got cruft from other operations scattered in the middle of it. So what our call operation is, it gives a target address and a belt list. Not just 1 operand, not just 2 operands, but a long list whose length is determined by other matters that don't matter, but typically up to 16 arguments. And it says, I want that one and that one and that one and this one, and then I want this one again, and so forth. And all of that winds up being picked up off of the belt, and the callee gets a brand new, to him, empty belt with all the arguments in order. This takes place in 1 cycle. And how we do that is another talk. I think you've heard that before. This is also the way interrupts work. An interrupt is for us is nothing except an implicit, unexpected function call, and works exactly the same as our own function operation. The interrupt comes in, there's its arguments in the belt. The remainder of the belt is filled with invalid.
But you've got to put it back together again when you return from the interrupt.
Again, please?
You've got to put the belt back together again when you return from the interrupt.
As I said, that's another talk. Yes, you do, and as I said, there's not a whopping big shift register in this thing. Trust me, there is no big shift register. This is the programming model is that there's a big shift register, but there isn't one really. And actually, internally, what it looks like is sort of like a cross between a content addressable memory and a bypass network on a conventional machine. That's what it looks like internally in hardware terms, but that needs slides to explain. Yes?
So debugging must be fun on this machine.
Debugging must be fun.
Debugging.
Well, like anybody else, the bulk of the debugger's code you want to do wants to be line by line, and if it's been heavily optimized, it's impossible, and that's true for us too. JITs are more of a problem because the JIT has to produce whole EBBs, which many JITs don't, and we do not support self-modifying code at all of any kind. We've got to produce a whole new EBB and then get us to move the thing into the data path for the instruction cache. Anybody who does self-modifying code deserves it. The actual debugging itself at the machine level, if you actually do need to look at operations, yes, we have a debugger. If you are thoroughly familiar with the way the machine works, it's easy to use, and even one might say friendly. The interface is the same as GDB. We just copy the interface, not the code, but the way the interface works, with a few minor exceptions to deal with some things that GDB doesn't know about, like wide instructions. Dave Yost, wherever he is, there he is, designed, and we have put off implementing, a graphic debugger that would actually let you watch visually the execution of the machine, instruction by instruction as things went along. And we will probably do that at some point. But guys, we're a starving startup. We've got limited resources, and things that will be beautiful for end users need to wait until we have end users.
One more question. What
Yes?
about user and kernel mode protection issues?
Protection,
Yeah.
Not filed.
not filed. I can say that the machine is a static shared address model. It is intended to run a nanocore operating system. And what Steve Jobs thought he was going to do before he discovered that existing chips wouldn't do it right. Yes, it's got very interesting protection characteristics, including, among other things, that it is immune for a large number of common exploits that are simply not physically possible.
So capabilities or
Hmm?
is it some sort of a capability architecture?
It is not a capability architecture. I would love to do a capability architecture. I think the caps are the most wonderful thing in the world. I know how to build one, and I don't know how to sell one. We're in the goal to make money.
John, last?
Okay. You mentioned that interrupts were handled the same way as calls. In one interrupt model, interrupt just as a hardware invoke call, it returns to where it was. But there are a lot of other cases where you might have to save state and restore state and switch among threads and do multitasking or multi-user support or exceptions that may return where it was or may return to a handler. So what is the machine state? Is it possible to talk about or to characterize in order to completely encapsulate where you are, go to something arbitrarily different, and weeks later come back and resume with everything in the original
Of course,
state?
it's general purpose code. You want coroutines, you want multi-thread, you want parallel tests. Yeah, we do all of those securely. The target is the code that you're using every day. The quantity of state in the machine depends on what model it is. A machine like that Gold with a large number of functional units, some of which have got large quantities of in-flight state. You know, you got a bunch of multipliers and things halfway through a multiply. And that state, there's the belt itself, the belt contents itself, but belt sizes, the smallest belt on our smallest member is 8 long. Most of them are 16, some at the high end are 32 long. But compare those numbers compared to the number of rename registers or even physical registers. What has Itanium got for a register count? Like 400 or something ridiculous like that. All of which is state that has to be saved. No, we don't do any of that. It's a quite low state machine. And deliberately done so. We wanted to keep things simple, and you got enough state, and you're paying in wire length and heat. It does.
3 seconds. The I-860 failed because they could save all the machine state, but had no way to restore it properly because of all the pipelines they couldn't access.
Yeah, well, it's smoke and mirrors. The Spark and the more recent Itaniums have the right idea, and that is that programs have got no business mucking with state. That hardware should muck with state because hardware knows what the state is. And the biggest single overhead in most codes on most machines is the amount of work you have to do a call, the preamble of the call, and the call, the preamble in the inside of the call, and what you got to do when you unwind it the other way. This is like a dozen instructions for one call up. This is ridiculous. So instead, do a call. Well, the hardware knows what you mean by a call. Give me a frame and save the state and this and that and the other. Let the hardware do it. No reason why the programmer has to muck with that, or the compiler for that matter.
That was VAX. A call instruction that did everything. And as you recall, MIPS was a reaction to the call instruction.
Well, if you consider that the VAX was done with flip cards, the major breakthroughs in our industry have been primarily breakthroughs not in architecture. Rather little of what we do was not at least foreshadowed by the IBM stretch. And this gentleman sitting here worked on the stretch, the 7030, and he is in our team, and he keeps our nose, he keeps young whippersnappers like myself from claiming credit for ideas that are in fact well known to everybody but me. The major advances have been packaging advances, not architecture, but packaging. The Data General Nova was the first computer that would fit on one circuit board on a 19-inch rack. They built a company out of that, a nice big one. The first processor that you could fit on a microchip, we call that company today Intel. The reason why RISC existed had absolutely nothing to do with the philosophical merits of RISC, which the arguments are pro and con, and they're valid arguments, both pro and con. The reason why RISC existed is that you could fit a RISC on a chip and you couldn't fit a non-RISC on a chip. That was a node window that lasted about 2 nodes, maybe 8 years. And after that, there's absolutely no excuse for a classic RISC architecture. And sure enough, they've all been migrating more and more cruft into it. Unfortunately, they're not doing it from restarting from scratch. So it's cruft on top of something else that wasn't intended for it, rather than doing what we are. We've got the luxury of being able to rethink this thing completely from scratch. We have got no compatibility, either mental, emotional, philosophical, or architectural issues. And when you go back and rethink something from scratch, you wind up with something like that, which is kind of different.
Cool.
Can we get rid of this light? Is it all possible? Or are other people not getting glare off the screen? Excellent, much better. That number 33 is just completely beyond what existing chips do. Your x86 max out at 4 or 5. Some chips, well, the TI goes up to 8. The upper limit of anything commercial I've ever seen is like 10 or 11. That can be issued simultaneously. Why on earth would you want to put out 33 ops? Well, the answer is that even in general purpose code, 80% of all the code is in loops. And if you can software pipeline those loops, which of course is what all the DSPs do, then you have in fact unbounded ILP. You can soak up every adder you can throw at it forever. But in current state of the art, rather few general purpose chips can be pipelined, at least on conventional architectures. The solution: find a way to pipeline almost all loops. And we have done that, but that's not the subject of today's talk. And throw hardware at it. Few people realize that how little of a chip's area and power are consumed with the actual functional units, the adders and multipliers and things like that. 6% of the total chip is the usual number for that. You could double the number and still be only at 12% of the chip. The constraint is not that you can't fit more adders and multipliers on. The constraint is that you can't interconnect them and you can't feed them with instructions. This talk is about feeding them with instructions. Once you have done that, well, you've taken care of the loop part of the problem. Amdahl's law still exists, and we handle the open code, non-loop code as well, but that also is not this talk. So, if you're going to try 33 operations per cycle, peak, how are you going to do it? Well, of the various possible bottlenecks within the machine, by far, actually, the biggest problem is decoding this stuff. There's two basic models for instruction layout. You can have fixed format instructions, where every instruction is the same length, your typical RISC instruction set. They are dirt easy to parse. You just drop the thing into a decoder, and the next one into a decoder, and the next thing in the decoder, and away you go. Bob's your uncle. But if each instruction is 32 bits, and you have 33 of them, the total space is 132 bytes. That's over 2 cache lines at 64 bytes per cache line. And you're simply not going to be getting 2 cache lines per cycle out of your top-level instruction cache. So that's pretty hopeless. It's an ouch. The other side of that problem is instruction cache pressure. You can't have unlimited instruction cache. Everybody needs more instruction cache, but the bigger they are, the further they are from the functional units, and the longer they take, and you start paying in your cycle time. Well, if you have a typical size of a 32K instruction cache, and they are occupying 132 bytes each, you only get 248 instructions in that cache. And as a rule of thumb, you need at least 1,000 instructions in your top-level cache, so we're a long way from that. Now, the alternative is variable length instructions, like your x86 instruction set. They are hard to parse. Intel is very, very good at heroics. And they throw hardware, and they throw power, and they throw everything else at parsing, and they only are able to decode 4 instructions at a time, and then only if it's a restricted subset of the instruction set, because if some of the really lollapalooza instructions in the x86 instruction set, you get 1 out, maybe. So, we actually have got a very compact instruction set in coding, and we run around 15 bits per operation per add per month. Now,
Freon?
one more example. This one's got 1 core, issuing 8 operations per cycle. Clock rate of not quite 500 megahertz. Only 1.1 watts. Am I in the way of people seeing this? I can move over if it would help. Only 3 gig operations, but also only $17. Anyone want to guess what the architectural category that chip belongs to?
Is it a DSP?
It's a DSP, and in particular, it's an in-order VLIW DSP, and it is a Texas Instruments DSP. Now, in abstract terms, these two are very, very different. But if you compare them, which is better? Well, it's apples and oranges, of course, but over the last decade, the industry has sort of consolidated itself into an accepted figure of merit, which is a good rule of thumb. That figure of merit is performance per watt per dollar. And obviously, you do need certain other things. You need the I/O complement that you have and everything else. But just for purposes of general comparisons, this has become the standard. Now, There's our two cores, our two chips. And the out-of-order superscalar is your half a MIPS for your watt and your dollar. The in-order DSP gives you 195 MIPS for your watt and your dollar. It's a factor of 400. Now, you'd think that by now somebody would see a market opportunity in this and tried to arbitrage that number away, but that difference has been around for a long time. So why is there a 400x difference? One is simple. The Texas Instrument chip is a 32-bit chip. If you want to do 64-bit addressing space, you need the superscalar. Another is total raw horsepower. It takes an awful lot of those Texas Instrument chips to add up to the total number of ops that you can get through the superscalar. But what really makes the difference is that the workloads are incompatible. The TI chip running on a general purpose workload is truly awful. It is designed for things which stay in loops forever, software pipeline loops, and code that is just full of random flow of control and random memory references, which is characteristics of your general purpose code. It tends to be very bad on. Now, the Intel chip would make a fairly decent DSP if you could buy enough Freon. So, the fundamental problem is the signal processing is not the same as general purpose, which defined our goal and our technical challenge as a company when we started out to design a new processor from scratch. We wanted to provide DSP numbers on general purpose workloads. Well, the numbers I'm about to give you are coming out of SIM or our best guess for marketing. We do not have something which is actually for sale at this point. Take it with a large grain of salt. The particular chip is 2 cores, issuing 33 operations per cycle each at a clock rate of 1200 megahertz, using 28 watts, and producing not quite 80 giga operations per second total. And our best guess is $85, although there's a gentleman sitting over there who probably may have a difference of opinion. That's our gold CPU architecture, one of several. I said it was a family, and in fact a dual core one. And you're getting 33 MIPS per watts per dollar out of that configuration. Now, in that list of what gold does, you may have noticed that. Thank you. Good afternoon. This talk is mostly addressed to the high end of the mill CPU family. It's a family in the sense that the 360 is a family. And at the low end, the kinds of issues that he speaks of are essentially not a problem. I mean, an x86 can decode 4 instructions in a cycle. If all you need is 4, this is established art. It's when you're at the high end and you need to pull a whole lot more. Other talks, other times, or questions, I can remark on what we do at the low end. They are equally innovative as what we have here. This being a university class for credit, we'll do the traditional and start with a short quiz. You all know the various kinds of architectures. There's accumulator machines and stack machines and this, that, and the other. So if I give you a set of specifications for an existing chip, can you tell me what architecture that chip is? One is, incidentally, this is an existing top-of-the-line product from a major manufacturer. 4 cores, each one of which can handle 4 operations per cycle. You may need Freon cooling. 3,300 megahertz, Using 130 watts, that's where the Freon comes in. 52 giga operations per second for $885 list. Anyone want to guess what the architecture of that chip is? Don't all speak at once. Someone? Yes,
Some random 8086.
but the architecture, not,
The architect.
what is this organized? Is it a stack machine?
It's a register impoverished machine.
I'll take that one. It is, in fact, a general purpose out-of-order superscaler, which, in particular, is an Intel Xeon.